Hello everybody. We're going to have a look at some application questions for circular functions today, and these are really good to do because they really test out whether you fully understand the whole concept of circular functions from woe to go, and it's great practice. So what I suggest you do is when I reveal the question on the screen, I think it'd be great if you could just pause the video and then have a go at the question in its entirety and then come back and we can discuss it, because that way you will learn the most that you can possibly learn by making the mistakes if you're going to make them and then learning from them. The learning once you make a mistake is twice as powerful as the learning if you don't make one, if you know what I'm trying to say. It's a tremendous advancement tool, is making a mistake. So let's do that, shall we? Now what do we got here? It's suggested that the height h of t meters of the tide above mean sea level on the 1st of January at Warnang is given approximately by the rule h of t equals 4 sine pi t over 6, where t is the number of hours after midnight. Okay, I can get that. Tides do move in a sinusoidal way. They certainly do. In A, we've got to draw the graph for t is 0 to 24 hours. We've got to then tell them when was high tide in B, and then in C we've got to find the height of the high tide. In D, what was the height of the tide at 8 AM? Pretty straightforward so far. And then E, our boat can only cross the harbour bar, sandbar thing, when the tide is at least 1 metre above mean sea level. Okay, so when could the boat cross the harbour on the 1st of January? Okay, I think I get that, don't you? That's a bit knotty, but we can sort it out for sure. No problem. Now, come on, pause and go and come back, right? I'll wait for you. Okay, you're back. How did you go? Did you get it okay, or did E create some problems for you? I'll talk about that in a minute, but let's go and do the question. So here's A. H of t would be 4 sine pi t on 6. Now I'm just going to do some diagnostics on this so I can get a feel for when I need to graph the thing, okay? The amplitude's 4. The period is 2 pi over pi on 6, which would be 12 hours, and that makes sense for tides anyway, because you do get 2 high tides a day, 2 everything tides a day, 2 cycles a day. A quarter of a cycle therefore would be 3 hours, wouldn't it? And the starting point, there's no horizontal or vertical translation, so the starting point would be 0 and 0, okay? That's pretty easy. And there's the graph. So that's a pretty straightforward graph. Here it goes, there's one cycle after 12 hours, the other cycle here over 24 hours. The amplitude's 4, quarter cycle is 3, everything's good. So we're off to a flying start, aren't we? Okay, B. High tide occurs, yes, when t equals 3 and t equals 15. Now, it's sort of a little bit unclear when they say when was high tide. Would that be an appropriate answer, or would you need to quote the time of day? I think I'd probably quote the time of day, just to be on the safe side. Or I'd probably quote both, actually. So I'd say when t is 3 and t is 15, but more particularly I think I'm leaning towards 3 AM and 3 PM. Okay, put a box around that. Alright? Now, what was the height of the high tide? Well, that's an easy mark, isn't it? Goodness. 4 metres above mean sea level. Yes? Good. What was the height of the tide at 8 AM? Well, I think we just need to plug t as 8 into the equation and work out what you get from that. And okay, yes, of course. T is 4 sine 4 pi on 3 if t is 8, that's right. Now, that's an exact angle which we know the value of. That's in quadrant 3, isn't it? So it'll get you minus root 3 on 2, which gets you an overall answer of minus 2 root 3. Okay? Well, we're cooking. Now, what are we going to do now? E. E looks a little bit knotty. So, yeah, we've got to work out when the tide is exactly 1 metre above mean sea level. Now you can just imagine, if I did a graph of y equals 1, it'd be zooming along there like that, wouldn't it? And you can see that it's going to cross the curve, intersect with the curve 4 times, and this hump from here to here, that one there from there to there, that'll be the first time interval, which is okay to get into the harbour, and also the second one will be where it crosses, say, here to where it crosses there. And we'll also include those times and in between those times, because you'll notice that it said that it has to be at least 1 metre. So there, see that word at least? So therefore it's 1 metre and above. So right, that's what we've got to do. We've got to lock in those times when it equals 1 metre, and then say, well, it's those times and in between those times for both occasions where this occurs. Yes, over the 24-hour period. All right, you got it? Okay, so that's if 4 sine pi t on 6 equals 1, we can solve that, and we get that, yes? And yes, now I've got to do a working domain here, guys, if I'm going to work out all the occasions where it occurs. So if t goes from 0 to 24, then what's pi t on 6 going to go from? See, I've got to capture all my solutions, and I need to know what the working domain is in order to do that. Okay, so pi t on 6 would go from, if you multiply both sides of this thing here, this term and this term by pi on 6, okay, to get pi t on 6, you'll get 0 to 4 pi. So that encourages me, because it shows me it's 2 cycles, and this looks exactly what we were getting here. 2 cycles, probably 4 intersections, yes? And that's 2 quadrants in which it's going to be positive, so everything's looking good. So in quadrant 1, I looked up on my calculator that the angle whose sine is a quarter is 0.253 radians, right? So when you draw a cast diagram, that's the quadrant 1 situation, and there's the quadrant 2 situation, both of which are applicable in this instance, because we want the angle whose sine is plus a quarter, okay? So what we've got to do is go zooming around here, this one, and then repeat the whole thing round for the second cycle to get us up to 4 pi, right? So there will be 4 occasions, 4 solutions captured, which is exactly what we suspected from the graph on the previous screen, which is marvellous. Now, here it goes. Pi t over 6 is equal to, yes, okay, what have I got? 0.253 pi minus that, then leapfrog by adding 2 pi to this one, and leapfrog by adding 2 pi to this one, and we get our 4 solutions, okay, when the tide is exactly 1 metre above sea level, right? Now we've got to multiply both sides by 6 over pi. My oh my, oh yuck, I want to die. No, we'll be flying high when we turn this into decimals, which I think we have to do because it's looking pretty desperate, isn't it? Ah, that looks better. That looks better. Now we've got to convert these into, well, you know, I think we need to convert them into time of day to really answer the question properly. So let's convert them into times of day. They're hours after midnight at the moment. So that's 0.483 hours after midnight, 5.517 hours after midnight, and so on. So that's 0029. I'm doing it in 24-hour, military talk and aviation talk. That's 29 minutes after midnight. Now that's 5 hours plus 0.517 times 60 minutes, which gets you to 0531 hours, and so on and so on. Now, therefore, these are the times when the tide is exactly 1 metre above sea level. So we want these times and in between those times as the applicable times when the boat can get across the sandbar into the harbour. So I say like this: hence the boat can cross the harbour from 0029 to 0531 hours inclusive, and from 12:29 to 17:31 hours inclusive. Now, were you careful enough to get that inclusive bit in there? Because, they did say at least 1 metre. If you said in between those times, I don't think that would be a correct answer. You've got to be very, very fiddly when you do these things and be absolutely precise, because the hawk-eyed examiners are just waiting to pounce on you, and you don't want to give them that opportunity. No, not at all. Never, ever, ever. Okay? So how did you go? Did you go okay? Did you get it pretty well right? Or did you get a little bit messed up with this last section and the times of days and the inclusive bits and all the rest of it? Did you have trouble converting these things in these beasties here into times of day? Well, hopefully if you did, you've got some learning out of that, okay? Okay, very, very excellent. A nice little title question. Done and dusted. And there's another box, which shouldn't be there. Oh, goodness me, I'll get rid of that box. Now, here we go. Next question. What do we got here? Now, this, oh yes, this is a Ferris wheel question. Passengers on a Ferris wheel ride access their seats from a platform 5 metres up above the ground. I think they're nuts. I'm the ultimate chicken, guys. I'm not going on it. No way. In my city, there's a gigantic one just been constructed, which you just go up into the stratosphere, and I'm not going on it anytime soon. As each seat is filled, the Ferris wheel moves around so that the next seat can be filled. Once all seats are filled, the ride begins and lasts for 6 minutes. The height h metres of Isabel's seat, Isabel, you silly girl, above the ground t seconds after the ride has begun is given by the equation h equals 15 metres. Ugh. Isabel, you're mad. 15 sine 10t minus 45 degrees. Now, this is the rotten part about this question. It's degrees. It's not radians, it's degrees, okay? So we've got to rejig all our thinking into degree mode. Plus 16.5, okay? So the central axis about which this thing gyrates is 16.5 metres up in the air. Ah! Let me out of here. So, first of all, we've got to use a calculator to sketch the graph of the equation for the first 2 minutes of its ride. I think they're doing this thing in seconds. Didn't I see that? Yes, seconds. So that's going to be, what did I say? 2 minutes, is it? Yeah, 2 minutes is 120 seconds, yes? So we've got to do that. And now what else have we got to do? How far above the ground is Isabel's seat at the commencement of the ride? Yeah, we can work that out, I think. C, after how many seconds does Isabel's seat pass the access platform? Oh, it's probably doable, I think. How many times will her seat pass the access platform in the first 2 minutes? Probably also doable. If we had a graph, it'd be nice and easy. E, how many times will her seat pass the access platform during the entire ride? Well, that's probably also easy. If we have a... maybe we need a graph of that. I'll think about it. And during during a malfunction, that's why it's a bad idea to go on this silly thing, Isabel. During a malfunction, the ride stops abruptly. Abruptly, did you read that? Abruptly, 1 minute and 40 seconds into the ride. Oh goodness. Isabel is screaming, the fire brigade's here, pandemonium's broken out, the television news is there, oh dear. How far above the ground is Isabel? Stranded. Poor girl, she's screaming, she's hysterical. Quick, get some sedatives ready. Send her to hospital for observation. And apparently in G, her brother Hamish was stupid enough to go on the thing as well. 1.5, he had a seat 1.5 metres above the ground at the commencement of the ride. Oh. So he was in a different car to her, right? Probably it wasn't cool to travel with his sister. How far above the ground is Hamish stranded? Well, I'm not sure about that one because that seems like a bit of a difficult one. We'll have to think about that. But let's go for it. Come on and see what we can find out. It doesn't look like it's too impossible, but the degrees thing's a bit of a irritation, isn't it? Okay, so A. Now we need some diagnostics before I can sketch this thing. So yes, you see how I've made a very big point of highlighting this degree bit because that's nasty. Yeah, so instead of the period being 2 pi over n, where n is 10 in this instance, the period's not 2 pi anymore, it's 360 degrees. So the period is 360 over 10, which is going to be 36 seconds. 36 seconds to go around this thing, this horrible thing. Okay? Now, I've put in red there that you need to put the graphing angle settings in your CAS handheld to degrees, because if you don't, you're going to get it all wrong. And you always should have your handheld device defaulting in radians, because that's the predominant variable that we use in trigonometry and circular functions, okay? It's very important to have it in radians, but if in this instance you better convert it to degrees to make everything doable and not drive you around the twist, okay? Now there's the graph. Woo! I've drawn in these some vertical values there on the vertical axis to make it easier to see. Look, they're going to be 30 metres, more than 30 metres up in the air. Oh, that's a bit of a scare, being that far up in the air. And there's the central, is that the central axis? Yes, I think so. Wait a minute, have a closer look at that. Yeah, 16.5, that's right. I always like to draw that central axis in so that I know I can see what I'm doing, guys. So I think we've done that. That's part A done today, hooray, isn't it? Yeah, the first 2 minutes, that's 120 seconds. Yeah, everything's good. Everything's good. Okay, very good. Now, let's go on now. How far above the ground is Isabel's seat at the commencement of the ride? Well, that's just t equals 0, isn't it? I think so. Yes, righto. Very good. T is 0. Now, sine of minus 45 is minus sine 45. Sine 45 is 1 over root 2. So it's going to be minus 15 over root 2 plus 16.5, which comes to, apparently on the calculator, 5.89 metres at the commencement of the ride. Okay? Yes. And apparently at that stage, Hamish is at 1.5. Okay? From that nasty question G. Righto. That's A and B done. And done very well, I think. Let's see what C is. After how many seconds does Isabel's seat pass the access platform? Well, the access platform was at a height of 5, wasn't it? So we probably need to do that. Yes? Now, it's a little bit difficult to work this out. See, that's... You could get many different solutions for that unless you restrict the domain, because, you know, sine functions cycle on forever and ever and ever and ever if you don't have some specificity in the solution. So I suppose really what we could do there is we could solve that on the calculator for the first cycle. We could restrict it. We could do a solve for sine equals all that thing, for t going from 0 to 36 seconds, because the period was 36 seconds. That would do it, wouldn't it? Because you'd have to pass the access platform over the course of a cycle, obviously. So that would do it, or you could do it graphically, which would be a nice, simple, easy way of seeing what you were doing. Yeah, I think so. I think that's the best way to go. So just proceeding on, we get that. So therefore, yes... So we're saying that sine of 10t minus 45 degrees is minus 0.76. So we need the quadrant angle. We need the base angle, which has a sine of 0.76, I think. Or we could just solve it for the CAS, or do it graphically. I think it might be easier for us, rather than trying to strain our brain working out which solution we want. Yes. So I think over the page, and I'll show you the calculator way that I did it first. There it is. Solve sine of 10. I've used x minus 45 equals minus 0.76 repeating, where x goes from 0 to 36. Now that just obligingly came out with two values that she's passed, 2 times at which she's passed the access platform in the first period of the first 36 seconds. And that's nice. Now, look guys, if you don't restrict the domain when you're doing solves on sine, cos and tan, you'll just end up with algebraic mayhem, with stuff all over the place and variables and general solutions, and it's just really difficult to read. So do get into the habit of restricting your domain for your solutions of trig solves. Yeah? Now, a little caveat here, you have to ensure that the angle is set to degrees in the document settings, because this is in the document part. If you've got a TI handheld, which I have, then you need to you need to change the graphing angle to degrees in the calculator section, and then if you do it graphically, you also have to change the graphing angle to degrees as well. You have to change it twice if you're going to do calculations plus graphs solutions of it. Alright, so therefore, having done all that, yes, I've got t is 27.51 seconds. That's the first time that she passes the access platform. There, and that's the graphical approach there. I basically did the graph, and then I did a graph of y equals 5, and I found, by doing analyze graph and intersection points, found the first solution, which was down here at 20. It's the same point, 27.5 seconds. Yes, there it is. Yeah. So that's probably the best way to do those. But there's lots of traps in all that. There's lots of traps in all that. Yeah. D. How many times will her seat pass the access platform in the first 2 minutes? Well, that graph on the previous screen was the first 2 minutes. So it looks like it's the easiest way to do that is have the graph and just rattle it off. 1, 2, 3, 4, 5, 6 times, right? That's going to be 6 times, right? Very good. Now, E. How many times will her seat pass the access platform during the entire ride? Well, you could do the graph of the entire 6 minutes and then just count them up, like in this kind of a situation here. Or, actually, I did this a different way where I just worked it out by logic. Because, you see, there's clues in this question. You've got to be awake to looking for clues. See, the thing goes for 6 minutes. The ride goes for 6 minutes. 6 minutes is 6 times 60 or 360 seconds. The period of the thing goes for 36 seconds. So in other words, there's 10 periods or 10 cycles during the entire ride, each cycle of which she passes the access platform twice, right? You can see that she passed it twice, right, in the first period, because the first period just ends here, the equivalent to point 2 over there, which is where she started, right? So one cycle further on is here, she's passed it twice, which makes sense anyway, obviously it does. Now, because, you know, her lowest point is 1.5 metres above ground and the thing is 5 metres above ground, so she's going to pass it twice, once on the way down and once on the way up again. Anyway, so one period is 36 seconds, entire ride 6 minutes, she has 360 seconds, therefore 10 periods in one full ride, and therefore twice in each cycle, therefore 20 times overall she passes the access platform. So you didn't even need to draw a graph, but you could draw a graph if you didn't see that, no problem. But just just have your radar up, you know, and be alert to the clues, because they're there, they always put them there. You've just got to basically have enough confidence to interpret the question in the easiest possible way to make life simple for you and not time consuming, because time is of the essence in exams. Right, how far, this is the fire brigade. Poor Isabel, she's screaming so loudly we can't hear ourselves think here. How far above the ground is she stranded after 1 minute and 40 seconds? Well, I think that's 60 plus 40 is 100 seconds, so we just plug that into the formula for Isabel, and we'll see how far the poor darling is above ground, screaming her lungs out. And there it is, 100 seconds, and there she be. And, I solved it on the calculator. 4.21 metres she's stranded. That's not too high. Heavens, Isabel, calm down, girl. 4.21 metres isn't too bad. Oh dear. Anyway, she'll get rescued soon. And G. Now this is a little bit more knotty, this thing, because he's in a different car. So you can't use the same equation for Hamish. He's in a different car. In terms of the mathematical formula for the height above the ground, Hamish is horizontally translated in his sine graph compared to Isabel because he's at a different point in the cycle. Same cycle, different point on the Ferris wheel, right? So this term here, this 45 here, is going to be different. Everything else is going to be the same, but that thing there is going to be a different term. Now I thought about how you could find what that is, and I thought initially I might have to just make it some pronumeral and then try and solve for it somehow. But then I thought, there's a marvellous clue. They said that he is at 1.5 metres above the ground at the commencement of the ride. Now, it just so happens, guys, if you had your radar beeping away there, you'd realise that 1.5 metres is exactly the minimum height point of the travel of that Ferris wheel. It's at the bottom-most point of its trajectory, okay? Now that is very significant because that means, if you think about that, you take a sine graph. Now just visualise that in your head now. You've got a sine graph starting at the 0 point like it normally does. Now I want you to translate it forwards to the point where, now at the 0 point, you've got the lowest point there, sitting there on the 0, right? So you've moved it basically exactly 1/4 of a cycle forwards, right? So that it now looks like an upside down cos graph, right? But the point that I'm trying to make is here, if you move it 1/4 of a cycle forwards, what you now have sitting on the 0 point, or the H or the Y axis if you like, basically you've got the lowest point, the lowest trajectory point of travel sitting there as your H intercept, which equates to 1/4 of a cycle moved horizontally to the right. Now, that means I automatically know that the period of this thing is 36 seconds, and therefore 1/4 of that is 9 seconds. So if you basically have this, I've jumped the gun, but that's what I was trying to say there, right? Now, therefore, what I put in this graphic, this section here, if I had a 10 and then had a bracket there, before for Isabel it would have been t minus 4.5. Well, for Hamish, it's going to be t minus 9. And we've got Hamish's equation here. And just remember, this is Hamish's equation. Maybe I should have put a different symbol there for Hamish, but look, you get the idea. This is height. This is h for Hamish's height, all right? And we can now solve it for the t is 100 seconds, and it's just going to fall out so easily for us without any trauma at all. So, but that's because we had our radar up and we looked for the clues, right? So there it goes. And where is Hamish? Well, Hamish is in considerably worse shape than Isabel. He's stuck 13.9 metres above the ground. But fortunately, Hamish is a guy, and guys don't scream, okay? He's just closing his eyes and gulping. Waiting for the fire brigade. All right, that's it, guys. That's it. We had a good time, didn't we? And there's a lot of stuff in there for you to sort of think about and take in, and little traps that you will now avoid in future when you're solving these questions. Look, and do plenty of practice. Practice makes perfect, and perfect makes a very, very good exam score and a happy student, all right? So I'll see you next time for the next very exciting installment. Okay, bye for now.